Okay, so you're facing this complex task, right?
Yeah.
Maybe automating some fiddly process or just trying to get rid of something repetitive that drives you crazy.
Uh-huh.
And you think, AI must be able to help here. But then instantly it's like, where do you even start? Do you grab one of those huge general language models everyone talks about, the LLMs?
Yeah, the GPTs, the Gemini.
Exactly. Or is there maybe another way, a different approach for, your specific problem?
That feeling, it's so common right now. The AI potential is massive, but actually getting it to work well on a niche problem, especially when you need outputs that are like structured and precise, that's tough.
Totally. And that's why this research from ServiceNow really stood out. They basically tackled this exact problem, a really practical one, generating low-code workflows automatically, just from someone describing what they want in plain English.
It's a perfect test case, isn't it? It lets them ask that fundamental question. For a task needing deep domain knowledge and a structured output, what works better? Clever prompting with a big general LLM. Or taking a smaller language model, an SLM, and really drilling it, fine-tuning it on data specific to that exact domain.
That's the core question we want to dig into today. We're going to unpack their paper, look at how they did it, the data they used, and crucially, what they found out.
And why does it matter? Because the answer, well, it has pretty big implications for anyone trying to build AI tools for specialized areas. Think finance, healthcare, manufacturing.
Or enterprise IT automation, like in this study. So let's get everyone on the same page. What exactly are these low-code workflows they're talking about?
Okay, yeah, good starting point. Think of them like visual recipes for automating stuff. Instead of writing code line by line, you often use a drag-and-drop interface.
Right, connecting blocks that do things like look up a user record, send an email notification, update a database field.
Exactly. They're meant to be easier than traditional coding, but you still need to know what you're doing to build them correctly. You need to understand the system, the process logic.
It's not trivial. And the goal here, take a description like, when a user account goes inactive, find all their open incident tickets and assign them to the user's manager.
Right, take that plain English.
And turn it into the structured thing, maybe JSON or something similar, that the low-code platform can actually understand and run.
Exactly. Generate the executable workflow representation.
Okay, sounds simple enough when you say it like that, but I'm guessing it's actually really hard for an AI.
Oh yeah, definitely not simple. The paper lays out some key challenges. First off, the building blocks, the available steps or actions, they're not universal. They totally depend on the specific system you're working with. A company might have added custom steps, custom integrations. The AI needs to know the exact menu available there.
So it's not just a generic send email step. It might be the send notification via company system X step.
Precisely. And then there's the structure. The workflow has to follow strict rules. You can't just, stick blocks together randomly.
Needs logic.
Yeah, there are patterns. If you use an if condition, you might need a corresponding else. If you're processing a list, you need a for each loop structured correctly. Get the structure wrong, it just fails.
Like syntax errors in regular code, basically.
Kind of, yeah. Good analogy. Then there's the data flow between the steps. One step produces an output, maybe a list of user IDs.
Right.
The next step needs to know how to grab that specific list and use it as its input. That connection has to be right.
Okay, so step 1 finds incidents assigned to Bob, and step 2 needs to know to use that list, not just any list of incidents.
Yeah, exactly right. And maybe the trickiest bit for an AI. The inputs for many steps need super precise references to the system's data. The exact technical name of a database table, like incident versus problem or sysuser.
Or the column name, like assign to versus assignee.
Yes, get that tiny detail wrong and the whole thing breaks. The AI needs not just the general idea, but the specific technical identifier used in that particular system.
Wow, okay. It's like asking me to write database code without knowing the exact table and column names for your database. I couldn't do it reliably.
That's a really good way to put it. It needs the abstract understanding and the concrete, specific technical context. So given all that complexity, the researchers went down those two main paths we mentioned.
Path 1. Let's try the big guns.
Okay.
The LLMs, GPT-4o, Gemini, the models that seem to understand language so well. The idea is you just describe what you want, right?
That's the hope. But, as the paper points out, for tasks like this, needing structured output, needing domain specifics, just a simple prompt usually isn't enough.
Right. They had to get more sophisticated. So what did they do?
Well, they use an approach called task decomposition, instead of asking the LLM to generate the whole complicated workflow at once.
Which might be too much to ask.
Yeah. They broke it down. First, they prompted the LLM to generate just the high-level outline of the workflow, the main steps, the basic structure.
Okay, like a plan.
Exactly. Then, as a second distinct step, they prompted it again to go through that outline, step by step, and fill in all the detailed inputs and configurations for each one.
Makes sense. Divide and conquer.
And crucially, they used retrieval augmented generation, RG. This is super important for domain-specific stuff.
Explain RE again quickly.
Sure. It means they didn't just rely on the LLM's general knowledge. They actively retrieved relevant, up-to-date information from external sources specific to the user's environment.
Like
The exact list of available workflow steps for that system, or the correct names of the database tables and columns they might need.
got it. And they fed this info to the LLM.
Yes, directly into the prompt. It becomes part of the context the LLM sees.
Ah, so the prompt isn't just build this, it's build this, and by the way, here are the allowed steps you can use, list, and here are the relevant table names. That list, use these.
Exactly. It helps prevent the model from making things up hallucinating and gives it the ground truth it needs for that specific system. These prompts ended up being pretty complex, dynamically built with all that RAG info, guidelines, the task definition.
Okay, so that's the LLM path. Sophisticated prompting, decomposition, and RG. What was path 2?
Path 2. Fine-tuning a smaller language model, an SLM. They specifically used Mistral Nemo 12B base. That's under 15 billion parameters, much smaller than the big LLMs.
Why smaller?
Potentially faster, potentially cheaper to run, although they do mention that cost gap might be narrowing a bit now. But the core difference wasn't just size.
It was the method, not just prompting.
Right, they fine-tuned it, which means they took that pre-trained SLM and essentially gave it further training, but focused entirely on a dataset built from thousands of real examples of these low-code workflows from their specific domain.
So it wasn't just learning general language anymore. It was learning the specific language, the patterns, the structures, the data references common in these particular kinds of workflows.
Precisely. Learning by example thousands of times over. They even structured the training data to match those two subtasks from the LLM approach, generate the outline, then fill in the details. And they fine-tuned the RAD retriever, too, to make it better at finding the right info for this domain.
Okay, 2 distinct approaches. Now, how did they figure out which one actually worked better? They needed good evaluation data, right?
Absolutely. And measuring success here isn't straightforward. Standard text metrics aren't really suitable for checking if a workflow is, functionally correct.
Right. It could sound right, but be totally broken.
Exactly. So first, the data. They used thousands of existing internal workflows to build their training sets. But they were smart about it. They realized existing workflows are usually complete and polished.
Whereas users.
Users often start with messy ideas, incomplete drafts. So they also created synthetic, simpler examples to better mimic how a user might actually describe a workflow they're just starting to build.
That's clever. Captures the real-world input better.
Yeah. For the actual evaluation, they used 2 key data sets. One was an out-of-domain set, or mode. This came from 10 different customer systems, different industries, like retail, banking. Meaning the specific steps available, the table names, they were different from what the fine-tuned model had seen in its training. This tested generalization within the broader domain, but to unseen specifics.
Okay, OD set. What else?
A test set. This one was cool. It was created by expert users who were pretending to be typical users of the application. They wrote requirements like real users might, sometimes vague, sometimes incomplete.
More realistic again. Okay, data sorted. How did they measure quality? You said text metrics don't work well.
Right, so they developed a custom metric. Flow similarity, or FlowSim. This is pretty neat. They represent the workflows not as text, but as tree structures. Think like abstract syntax trees in programming.
Okay, capturing the hierarchy and connections.
Exactly. Then they used a tree edit distance algorithm. Basically, it calculates the minimum number of changes adding, deleting, or changing nodes needed to make the generated workflow's tree structure match the correct one.
Ah, so a higher FlowSim score means the generated structure is closer to the target structure.
Precisely. And they checked this. They showed FlowSim scores correlated well with how human experts rated the quality of the generated workflows.
But wait, what about workflows that look okay structurally but are just wrong? Like using the wrong step. Does FlowSim catch that?
It captures differences in the nodes, steps, and structure, so yes, to an extent. But you raised a key point earlier. What if the structure itself is fundamentally broken, like an else without an if?
Yeah, totally unusable.
FlowSim might still give it a decent score if the rest looks similar, so they added another critical check. They measured the percentage of generated workflows that had basic structural errors that would make them impossible to run.
That seems essential.
Yeah.
A broken workflow is useless, no matter how similar it looks otherwise.
Totally. That structural validity check became really important in the comparison.
Right, the moment of truth, the results, prompted big LLMs versus the fine-tuned smaller SLM. For generating these complex workflows, who won?
Well, looking at the main metric, FlowSim, for the complete task generating the outline and filling in the details, the fine-tuned SLM came out significantly ahead.
Significantly, like how much better?
On average, across both the test and ODE datasets, the fine-tuned SLM showed about a 10% higher FlowSim score compared to the best results they got from prompting the large models like GPT-4o and Gemini.
10%. That's actually quite a substantial improvement in quality.
It really is. And interestingly, the gap was even bigger on that out-of-domain data. There, the fine-tuned SLM was 12.4% better on average.
Wow. So even when faced with system specifics it hadn't explicitly trained on, the fine-tuned model adapted better than the general LLMs just given the info via RAG.
That's what the results suggest. It seems like learning the patterns and types of elements within the domain during fine-tuning provides a more robust foundation for handling variations than just feeding specifics into a prompt for a general model.
Okay, that's FlowSim. What about those critical structural errors, the unusable workflows?
This is where the difference was really stark. TPT-4o, while performing reasonably on FlowSim scores alone, actually produced a lot of structurally broken workflows, over 17% on the test set.
More than 1 in 6 were just unusable.
Yeah. Compare that to the fine-tuned SLM, which had a structural error rate down around 5%. Gemini 2.0 Flash was also better than GPT-4o, around 7%.
So the fine-tuned model wasn't just closer on average, it was much more likely to produce something that actually worked.
Exactly. And when they recalculated the FlowSim scores, but this time counting any structurally broken workflow as having a score of 0.
Which seems fair, if it's broken.
Right. The fine-tuned SLM's advantage became even larger. It highlighted that it was producing significantly more valid and usable workflows.
That's a massive practical difference. A 17% failure rate is probably unacceptable in a real tool.
You likely couldn't deploy that. They also checked the impact of RAG quality. What if the retrieval was perfect?
Did that close the gap?
It helped all models, yes. Giving them perfect RAG data, the exact right steps, the exact right table names improved scores. But interestingly, it only accounted for a small part of the overall performance difference. The maximum gain from perfect RAG was only about 4 percentage points.
So the main problem wasn't the RAG system finding the wrong info.
It seems not. The bigger issue was the model's ability to correctly use the information they were given, to structure the workflow properly, and to put the right data in the right place.
It's like you can give someone the perfect recipe and ingredients, but they still need the skill to actually cook the dish correctly.
That's a perfect analogy. The execution was the key differentiator. And to understand why the fine-tuned SLM executed better, they did a deeper dive into the types of errors each model made.
Okay, what did that error analysis show? Where did each approach stumble?
This is where it gets really interesting. The fine-tuned SLM actually had more trouble than the big LLMs when the workflow involved complex structural logic. Things like nested loops, parallel execution paths.
So the general models, maybe because of their broader training on code and logic, handle the abstract structure slightly better.
Potentially, yeah. The SLM sometimes missed necessary steps related to these complex structures, but, and this is the crucial part, the fine-tuned SLM was significantly better than the LLMs at getting the specific input details correct.
Input details
Like setting up conditions correctly in if statements or configuring specific parameters within a step. And most importantly, it was way better at handling features that were unique to this specific enterprise system.
things only someone familiar with that platform would know.
Exactly. Stuff like handling custom service catalogs correctly, knowing about specific service level agreements, SLAs, built into the platform, dealing with proprietary date formats. The fine-tuned SLM just nailed these domain-specific nuances much more often.
So it's a clear trade-off visible in the errors. LLMs, slightly better on general structure, fine-tuned SLM, vastly better on domain-specific details and correctness.
That's a great summary. And their theory on why this happens makes a lot of sense. For those really intricate system-specific details, learning them by seeing thousands of examples during fine-tuning seems much more effective than trying to explain all that nuance and context in a prompt.
You can't easily write a prompt that covers every single specific rule and data type of a complex enterprise system.
Probably not effectively. The fine-tuned model essentially internalized that domain knowledge from the data.
They also found something about how users phrase things, right? Implicit actions.
Yes. That was really telling. The fine-tuned SLM was much better at understanding user requests where the necessary workflow steps weren't explicitly spelled out.
Like the example before. Find incidents and close them.
Exactly. A user says that, but the system needs to know that implies find records, then likely a for each loop, and inside that loop, an update record step set to closed. The fine-tuned SLM was much better at making those inferential leaps.
Which, again, probably comes back to the training data reflecting how people actually talk about these tasks.
Almost certainly. It highlights the need for training data that captures the natural, sometimes implicit way users describe things in their domain, not just perfect explicit instructions.
Okay, let's pull this all together. What's the big takeaway here for you listening to this, thinking about using AI in your own specialized field?
I think the main message is that while these big general LLMs are incredibly powerful and versatile tools, they aren't necessarily the best solution for every single problem, especially when your task involves generating highly structured output.
Like code or configuration files or these low-code workflows.
Yeah, and when it requires strict adherence to very specific domain rules and needs to correctly use data from complex, maybe unique external systems. For those kinds of jobs, this research provides pretty compelling evidence.
Evidence that.
Evidence that taking a smaller model and investing the effort to fine-tune it on a well-curated dataset from your specific domain can lead to significantly better quality, more accurate, more reliable, and crucially, far fewer outputs that are just fundamentally broken.
So it's a trade-off. Prompting the big models is easier to get started with, no doubt. Less upfront work.
For sure. But if you're hitting a wall on quality, or if errors are unacceptable for your use case, this study suggests that the potentially harder path of fine-tuning might be the way to unlock that next level of performance for specialized structured tasks. The investment in curating that domain-specific data can really pay off.
This deep dive really gives us a clear, data-driven example where going deep with a smaller model and targeted data beat going broad with a larger general model for specific demanding challenge.
It's a really strong case study, and it immediately makes you think, well, what about other domains? Could this apply to automating parts of, say, medical diagnosis based on patient records, or designing complex manufacturing processes, or handling intricate legal document generation?
Areas where precision, structure, and domain-specific knowledge are absolutely paramount.
Exactly. Could fine-tuning models on massive data sets within those specific fields be more effective than trying to coax a general AI into understanding all the nuances through prompting alone?
It really makes you wonder, where in your own field, your own work, might fine-tuning be that hidden key, the thing that unlocks truly high-quality, reliable AI performance, where the general models just aren't quite cutting it?
Definitely something to mull over.